What did this have to do with anything? That stochasticity video, right? The idea of randomness, chaotic, but more than random, it's like chaotic. It's like if you put a droplet of food dye in some water, it just spreads out. I mean, it's not really, I mean, it's natural, but could you get any useful work out of it? It's kind of, that's what it's kind of getting into, is this idea of work, right? And we're supposed to think of work as what motion that the system did to the surroundings? Ordered motion. So at that microscopic level, there's ordered motion. So the idea is out of all this energy in a system, it's kind of, not all of it can be used to do useful work, because some of it, a component of it, you just, and it's hard to draw the line here. Mathematically, you can do it with numbers, but conceptually, it's really hard. There's just a component of energy that it's useless. You can't get any useful work out of it. It's chaotic. It's good for nothing. You can't do much about it. So, and it's just a fact of life. So, they're trying to take that into account with these ideas that even though U is the entire, internal energy, is all energy in all modes, right? There's the entire energy of your system, your surroundings, your total, whatever you want to think about. But, and then they call A the maximum work function. And so that, I guess you could write it this way. Delta A is delta U minus delta TS. But they're going to say that delta A is constant, I think it was temperature and volume? Yeah, constant temperature and volume. So you really have delta U minus, you can pull that T out then because it's constant temperature, T delta S. So they're trying to say that, okay, here's your stochasticity, here's your chaotic component. Okay, so you don't get to use all of the internal energy to do work.
So is this delta A like equal to delta H sometimes?
Okay, so now you can substitute stuff in. See, if you want to relate delta A to delta H, we have this expression. So delta A, right? What was that? We had delta U is delta H minus T delta S, right? I don't know where it is, but it's in there somewhere. I don't remember. I'm too dependent on these cheat sheets. Delta U is, I thought it was delta H minus T delta S.
Yeah, I think so. Yeah, I think
Right?
that's right. Delta U is delta.
Yeah, so you could have delta H minus T delta S, right? Then you have another minus T delta S. So you can play around with this stuff. Okay, so you can get a delta H in there, but it's constant temperature and constant volume. So I think a more useful, because when is temperature constant? Hardly ever. So it's more, this one is more useful. That Gibbs. Okay.
Isn't it?
So I remember H is constant pressure. So if we have delta G, delta H, well, that's going to be constant temperature too. But just constant pressure. I think that's what the thinking is here you have, they're both constant temperature, but if you pick constant temperature conditions, so you can get a relationship, you can either have volume be constant also, or you can have pressure be constant also. And on the lab bench, it's a lot easier to, it's very, it happens all the time, constant pressure. So we see this much more often than we see the Helmholtz function. We hardly ever see it. Okay, but so what's the difference between the two? They call them maximum work functions, kind of like. So with delta G, it's down here. Maximum non-PV work for Gibbs. What was PV work?
I
Yeah,
don't know.
yeah, but PV work. This gas, it just kind of expansion or compression. And that's all we've been talking about, is that type of work. So it's kind of odd that delta G, the most common one, gives you the maximum work for all kinds of work other than PV work. Okay, so I don't think we're going to be playing around with this that much. It's just giving you some ideas of the energy and what's useful and what's not useful. Okay, but their criteria for spontaneous change, we're used to this, Gibbs being less than 0. But if you want to talk about constant volume conditions too, and then you could talk about Helmholtz. Okay. Yeah, we kind of talk about all that. So if you wanted a spontaneous change, right? Do you remember this? What conditions would you want looking at that expression? What type of, if it's a reaction, you'd want it to be, or a process, exothermic.
With a high delta S.
High positive or a high,
Positive.
yeah, so you want that entropy to be increasing, right? So you want delta S to be positive. And high temperature or low temperature?
High.
High, right? Now, sometimes you could, one can override the other one, but overall you want it to be negative. So there's not a whole lot to really harp on this section. We have, remember what these little things are, Alyssa? These little symbols? Yeah, stoichiometric coefficients. So that's their complicated way of saying you can get the Gibbs energy for a reaction by adding up all the Gibbs energy formation of the products minus all the Gibbs energy formation of the reactants. We know that. Okay. So we just put R's on. Well, let's not put R's on it first so you recognize it. So you can put R's on everything too. Okay. Make them standard so you can use tables. So likewise you could look, just like before, look up change in entropy for all the products minus reactants. Change in enthalpy. Heats of formation for all the products minus reactants. So that's kind of where they're coming from. So not a whole lot new today. So this is our last day. And then we have review on Friday. Review Friday, exam Monday. So I tried to spread this out, but like you can tell, there's not a whole lot to spread out here. There would have been a lot of homework to combine this with the last one. So, but this homework isn't so bad. Look at 17.
It's just what we've done before.
Yeah.
Just have to make sure your coefficients match up. Signs.
So there's not a whole lot to talk about there. Now, I wonder, I don't know, I just use delta G's, right? I looked up all the delta G's for products minus reactants,
Yeah.
right? Because I didn't go the hard way of looking up all these and looking up all these, and right? No, just use the delta G's. So not much to do there. Calculate the standard Gibbs energy of the reaction. Oh, here it is. Now you got to use the standard entropies and the standard enthalpies of formation, which is kind of silly. I've never liked these questions. I mean, why? You just use delta G. Fine. Just remember, watch your units. That's the trick to this. One's in joules. The other one's in kilojoules. So that's a common mistake, not to convert. You can't take apples minus oranges. Everyone with me so far? See what I'm talking about? You remember this? Gloriana, you remember this? Okay. 18, 19. Okay. Now we're getting into something a little more interesting, I think. Standard combustion phenol. Okay, we know what that will be. They want this standard Gibbs energy formation of phenol. That's a different reaction than this one. Seems to me, how would you write this enthalpy of combustion of solid phenol? Shelby, how would you do that?
Would you break down the reaction?
So how would you write this guy burning? What's the traditional way to write it? This,
That's the whole thing.
that whole thing.
Going to CO2 and H2.
Okay.
And you got O2.
Yeah, and then add an O2 over here. Now the subscripts are going to be important, right? If we're looking up all these guys. So it's O2 gas. Our phenol is a solid. CO2 is a gas. And it's supposed to be H2O liquid. All right, so see if you can balance that thing. Oh, they want us to do all that. I guess that makes sense. These problems are tough because how do you know what's available in the table and what's not? There must be stuff missing in the table. Because I had to go all the way down and use this. But they, well, let's wait. Let's wait. We're not there yet. They want the standard Gibbs energy of formation of phenol. So first off, we wrote this guy backwards. It's negative 3054. Right? If we want to get the standard Gibbs energy of formation of phenol, right? It's one of those games where you're going to be adding up reactions. Right? But the end product, what you want to get, is a standard enthalpy of formation of phenol. So that phenol is supposed to be where? Yeah, the product side. So I think we should have started. We should have started here, right? Because now we wasted our time. I know I'm upset because I always start with the answer. You always start with the answer, otherwise you waste time. So solid. So you can see right off the bat, we're going to have to flip this reaction. We'll have to flip it. We'll have to pretend it's flipped. But how do I write this final answer down here? For the standard, an enthalpy of formation reaction for phenol. What would be on the reactant sides? What has to be over there, Kevin? Yeah, all those elements. Yes. H2. C solid, I heard. And O2 gas. All right. Now remember the trick to this. How do you balance it? You have to have a 1 in front of what? Whatever you're forming. So in front of that O2, I have to put a half. I need 6 of these guys. I need 3 of those guys. All right. Okay. So we're going to have to make a big table of all this stuff. right? So this guy we're going to have to flip. And then we got to get rid of the CO2 and the H2O, so I guess we're only going to have 2 more reactions here.
I think we have those delta H's on our cheat sheet.
Yeah, we do, because they're so dang... Oh, but it's H2O gas, though. We need H2O liquid. So we'll have to look that one up. But you'll find the enthalpy of... So this guy has to be flipped. Oh, it's so confusing. I got to flip him, or I'm going to get so confused. Burning him, I'm getting CO2 gas and H2O liquid. So I need 6 of those. 6 times 2 is 5, 6. I need 3 of those. All right. 3 and 12 is 15, so 15 halves. Oh, that's not right, because I have one over there. 3 is 15. I don't need a fraction. Won't that work?
Yeah.
Did I do that right? Okay. So I've got a 1 in front of this. So that 3054 corresponds to that reaction. And it's positive because we flipped it. All right, I've got a 1 right there. If you don't have a 1 in front of that phenol, it's this 3054 is wrong. Okay, so then we'll have to do products minus reactants to get the delta S. See, I think that's why they gave us this. Something's got to be missing in that table, so we have to do it this way. So then you know what. So you do products minus reactants and get your delta S for that reaction. And you're going to need this number. And then we got to get rid of the CO2 gas. Right? It's enthalpy of formation reaction. We got to get rid of the H2O liquid. Right? It's entropy of formation reaction. And it looks like we're going to have to multiply this one through by 3. And this one through by 6 to get the stuff to cancel out on you. And then you get these guys. All right, see the game plan? And then once we have this nice little table all done, we'll add up all of these, put it in down here. We'll add up all of the entropies. Put it down there. And my T will be 298. So I don't like that question. It needs more English, saying why you have to do it this way. I guess you'd find it out default that you don't have the numbers you need to do it any other way.
What is the other way that you're talking about?
Well, they want to calculate the standard Gibbs energy of formation of phenol. So just do products minus reactants for this guy.
Right.
But something's got to be missing. The delta G, I think the delta G for phenol must not be in the table.
I see what you're saying.
But I don't.
So if it were,
just do.
we would just do.
If you were
delta
given
G
it of the
for
products
phenol
minus reactants.
Minus
Yeah.
3 times the delta G for H2.
Yeah.
Times 6 times.
Yeah.
Okay.
Or you just look it up.
You really only have to do the first one and look at the other two. Like for the phenol one, find the delta G using the equation, and for the other two, they should be in the book, the table for the carbon dioxide and the water.
Yeah.
Yeah, but we can't get we don't have the delta G for phenol.
Right, so you just do for that one. You get the exactly delta G for the phenol.
But that's all you need is delta G for the phenol. That's like your answer. So if you can get that, you don't need to do anything else.
Okay. So who wants to tackle 21? Calculate the entropy change. Monatomic perfect gas compressed to half its volume, simultaneously heated to twice its initial temperature. Sounds like what?
That's to half its volume. That's simultaneously. It's one of those where we do two
steps.
delta S.
Two delta S steps. This is a good concept preview question.
One with temperature and one where we know the volume. But we don't know.
Yeah.
We don't need to know. Just,
We could
just
do-
2 to 1 for the initial and final volume.
We could constant volume heating. So if we do constant volume heating, we'd go from what temperature to what temperature. So there's no numbers in here, so we need to use variables. And remember that it's natural log of these ratios, so they're just going to cancel out our t's. So we'll go from what to what?
1 to 2.
Yeah, I'll go from T1 to T2, but in our equation, T1 and T2 don't cancel. We need to relate T2 to T1.
Oh, so 2 to 1 T2 equals 2 T1.
There, right? Because then when you do the ratio, they're going to cancel out on you, the t's. And then step 2, we're at 2T1, right? We'll do I just say isothermal compression. Right? And we'll go from what V to what V. How would you say that? Alyssa, how would you say that? What V to what V? Right, so how could you set it up so your V's are going to cancel in that natural log expression? It'd be V1. Well, you can say V1 to V2, but like that won't work. Would be V2. Right. So my V1s will cancel. Do you see that? Okay. So that's about it.
If we wanted to like write it out a little more, T1 equals 2 T1. T2 is double T1. Okay.
All right. Everyone see how you get a
Yes.
number for this? We get a number. And they told you monatomic perfect gas, so you know what. Remember what CV is for a it's in here somewhere. Yeah, it's something like that. 3 halves R, 5 halves R. Where is that? It's not on the cheat sheet.
What?
For a monatomic perfect gas.
What's the monatomic of the gas? Like one of them's like 3 halves over. 3 halves
Yeah,
R.
CPM is 5 times R.
What's on the sheet?
Oh.
Oh, that's on the other sheet.
There's another sheet.
1133.
Oh, there it is. Yeah, it is. Huh. Yeah, I forgot we have 2 cheat sheets. So it's there somewhere. So you can calculate CVM. Okay. 22. Calculate the maximum non-expansion work. So what symbol are we after? What mathematical symbol are we after when they say maximum non-expansion work? A? It was just the I thought it was just the opposite. Non-expansion work is delta G. It's just the opposite of what we're used to doing. It's odd how the most common thermodynamic symbol we've been messing with is really for maximum non-pressure volume type of work. So you're just after delta G. So you probably just do what?
Delta G equals delta H minus T delta S, which we delta H and T delta and delta S for the table.
So that's one way. Or just, if it's available, look up the delta G's for products minus reactants. Right? Write the combustion reaction, and then just do delta G products minus reactants. Delta G's. I think that'd be the easier way. They have to be in the book. Right? Both ways would work, though. All right, this one we're going to leave this one for last. That one's a B.
I really think the last is easier.
It's horrible.
It's easy.
But, sometimes you skip them if they're easy.
It's horrible.
It looks horrible.
Okay. It's a lot of little tricks to that one. 4.6. It's 4.6. Oh, it's just another one of those? Look at that. That's horrible. Look at that, Gloria. This is my solution to the one we're skipping. I'm just scribbling everywhere. I don't even remember how the hell I did it. Okay, but the other ones should be easier. 1 mole perfect gas expanded isothermally for an initial pressure of 3 atmospheres. Well, if we don't get through it on a review day, yeah, we probably will. Maybe you can figure it out, though. We should make it extra credit, right?
That's okay. It's very nice of you, but
Okay, so we're finding all these symbols. 36.
it's just this is all stuff like we've been doing, right? It's reversible.
So there's some easy ones. Fill out the easy ones first, right? Fill out the easy ones first. Reversible and isothermal, you can get some zeros just by those 2 words. More than one.
Q is going to be it's isothermal. And
Now realize they have 1 delta S without a subscript. I don't know if they probably did that in the book too. Because we're almost always calculating things for the system. So that's why they kind of assume that you realize that's delta S system. So see if you can get, if I do them all, I won't have anything to do for our review day. Right? That one's 0, and then there's some other zeros. Delta S total, because it's reversible. So change in entropy surroundings is equal to minus change in entropy system. So what else is 0?
is Isn't work 0? W?
Well, we have an expression for
yeah.
we have an expression for
W equals negative NRT.
isothermal reversible work.
Uh,
Remember what it was?
Would delta H be 0?
Isothermal delta H and
T.
delta T is 0, but they're not asking for that one. Delta U,
delta U and delta H are 0
isothermal.
in isothermal. Okay.
Isothermal, yeah.
We need to like make a table of all these.
Yeah, but if I do that and make it that clear, there's no job security left. That's a really good idea, actually.
Right.
We should do that.
Yeah.
That would be a good test question.
Fill in the table.
You fill in the table.
That would be a good, open book test. I agree.
That would be and you could write the mathematical expressions to find each one. That's a really good test question, right? Because I've got a column, have a column for adiabatic, have a column for, and you fill in everything. Have a column for, now there's a reaction.
So wouldn't part of that be in our cheat sheet?
Not really. Not really. These zeros aren't in there, right? Like for a reversible process, delta S is 0. That's not in here. That's a concept.
That should be our concept question.
So if you can get W, you've got Q. If you can get delta S system, you've got delta S surroundings. How are you going to get those?
You've got delta S systems, you've got delta S surroundings.
Because delta S system equals minus delta S surroundings.
Oh, okay.
There you go.
Yeah, that's right. Okay.
Internal energy.
And then Q is going to equal W.
Q is going to not equal W. Q is going to equal negative W. Q is going to be negative W.
H plus PV.
Does the delta S for the system and the delta S for the surroundings always equal 0?
Well, in this case, they're equal to the minus opposite of each other
Right.
for any reversible process.
Any reversal, that's the...
They're always going to be minus each other. And remember the concept preview, we've got a bunch of expressions to get delta S. And again, it's a shortcoming. Delta S, we should have been writing SYST this whole time, but we haven't, and we probably should have. We should have gone back to the very beginning on concept preview and just write SYST on all this every time we wrote delta S, because it's always for the system. But we didn't. So you've got a lot. And we should have, because then we'd have a real strong feeling. I know how to get delta S system. It's just concept preview. I'm going to pick one or more of those. Right? Add up the steps and get it. Then you know delta S surroundings. Got it.
So we've got delta S systems, delta S surroundings.
How would you get?
Delta H.
Well, Q is inversely proportional to W. So Q equals negative W.
Yeah.
Q is negative W.
W equals negative NRT.
So that means you got to get one or the other. Which one can you get? W is,
Negative NRTL and VF will be
there it
You
is.
can get VF and VO from ideal gas law.
Yeah, there are enough. Yeah, it looks like there's enough info there. You got it. You have the moles. You have
Yeah.
initial and final temperatures. Yeah. You bet. You can get V1 and V2.
It's gonna be one of those weird like you get like NRT over V times NRT over V.
Just see if you can help each other out and figure this out.
So the only thing that's changing is pressure.
is yours, Kelly.
Yeah.
This is yours.
All of it?
Yeah. That's yours.
So your NRTs cancel off. I don't know why I just left it at work for doing that. When we are using W equals negative NRT, we have to use 8.314 as our R.
Yep.
Anytime we need to end up in joule.
Yeah.
How do you find these two?
Dr. Smith, V2, can you use the same temperature?
Yeah, 'cause it's-
You have to. It's isothermal.
Oh,
Yeah, if it changes its pressure. Are y'all finding W?
No, I'm finding the volume curve.
You're finding the volumes first to find W then?
Yeah.
For like,
WNX.
Oh,
You
yeah,
gotta find
yeah.
V2 over V1 to get LNA of NRT.
it's weird like, when you do the NRT, you sub in the NRT, it ends up being like P1 over P2 at the very end, you know what I mean? 'Cause you got
Oh,
like-
you solved it that way?
Yeah.
With the work expression where it's ln and vf over vi,
Mhm.
since like that value will be,
Now, shouldn't the-
do you have to convert it to
Can you?
meters cubed?
Here's a concept question
No.
that might get confusing to you,
Anytime
right?
it's like-
The pressure went from 3 atmospheres to 1 atmosphere. Now, what if I didn't give you very much information? Now, numerically, you can calculate the answer, but the pressure decreased by a factor of 3. So the volume should what? By a factor of what?
If the pressure decreased, the volume.
Oh, no, sorry. The pressure. Well, the pressure went from final of 1 atmosphere.
Pressure went from 3 to 1.
Initial is 3. So it went from a high pressure to low pressure.
Mhm.
So it decreased by a factor of 3. So the volume's going to increase by a factor of 3.
P and V are
Yeah, so if I wouldn't have told you the initial pressures and final pressures, just conceptually you could figure out that ratio. Right? That'd be another good
Wait,
exam
what do you
question.
mean? If you hadn't told us.
Yeah, if I wouldn't have told you hardly anything here about the pressures, just say that the pressure decreased by a factor
Oh,
of
yeah,
3.
You told us that, yeah.
Right?
We could, yeah.
And then no numbers, just decreased by a factor of 3.
Yeah, you could just do.
Then you can figure out the
We've done
volume.
problems like that.
Oh, have we? Okay.
Back in like the chapter 2,
Oh.
like that first term of the we got like negative 9 points in for W.
I got 2.7.
Oh shit.
Oh, it's negative, I forgot the negative.
And I didn't multiply by T. I multiplied by T.
I forget that all the time.
Right, T is,
No,
what?
for
T is
the
360?
work.
I got 300.
300?
What was the
Yeah.
temperature?
I didn't even look.
It's
300.
300.
Oh, yeah.
So it's whatever I got times 300. Yeah.
What'd you get?
Negative 2740, so like negative 2.6.